So the one of the things we're going to be asking, so what is the thing that's actually being conserved? We know something is being conserved because the person isn't actually touching the ground or doing anything except for his head. Yet he continues to spin faster. He's not pushing himself faster or anything like this. So it must be something that's conserved that's making him go faster just by changing basically where his legs are positioned. Um, we know we know of a couple things that are conserved. One is linear momentum. Well, obviously this isn't linear momentum being conserved because he's not moving anywhere. His center of mass is basically staying in the same place the whole time. It's also not rotational energy. This is a little less obvious, but he's actually putting energy into pulling his legs in, and so he's actually adding extra energy in. And so it turns out that the energy is not the thing that's being conserved as he goes along. You could also basically do this calculation and find out that that his rotational energy isn't being conserved in this process. It's actually increasing. His rotational energy is actually increasing. So there must be a new conservation law. Well, it turns out that the new thing that's being conserved is something called angular momentum. It just has the equation that we normally do angular momentum as L. I don't know why it's L, but it's angular momentum is just the moment of inertia, which we've already talked about, times omega. All right, so it's similar to rotational energy, but it doesn't have the 1/2, and the omega isn't squared. It turns out this is a conserved quantity in isolated systems, and this system is pretty isolated because the only kind of point of contact is his head, which is relatively smooth because he has that hat on. And so what we find is that the angular momentum at the beginning is going to equal the angular momentum at the end. So let's look at this a little closer. So we're going to model him in kind of a silly way, but it'll at least get the point across. We're going to just model him as two cylinders. You see, one I've just put around kind of his body and legs right there, and then the other one I've put around his body and legs there. And if you notice, just in looking at the size of the two things, we're going to say that that the second cylinder is about half the size of the first cylinder, which I think is approximately right. We know the moment of inertia of a cylinder is just 1/2 mr squared. And so one thing we can ask is, well, what happens to his angular velocity? What happens to omega as his I changes, basically as he brings his legs in? Well, let's think about what happens whenever he's getting smaller. So his radius is basically going down to half the size of what it was before. And if we look at the moment of inertia equation, we see that means that his moment of inertia goes down by a factor of 4 because there's an r squared, and so if we take r over 2 squared, we get r over 4. So his moment of inertia decreases by a factor of 4. If we know that the initial angular momentum is equal to the final angular momentum, or the other way to say that is I omega initial is equal to I omega final, and if we know that the inertia at the beginning is decreased by a factor of 4 at the end, that means that the final omega, the final rate at which he spins, has to be 4 times faster what it is when it was initially. All right, and that's kind of our final result, which is that by decreasing his moment of inertia by a factor of 4, he increases his angular velocity by a factor of 4, so he's spinning 4 times faster. And that basically explains what we see in this breakdancing video. I hope that gives you some idea about how angular momentum works. We'll do some more examples in class and one very exciting demo. And hopefully you'll get a feel for this kind of interesting concept that we actually don't see a lot in real life. The only other kind of times that we see it is maybe with ice skaters when they do their spins and they basically bring their legs in and start spinning a lot faster. Other than that, we don't see this a lot, and it's an interesting little thing that you're going to learn about in this class. All right, have a great day, and see you in class.